Hello students, this is Amrit Manandar. Today we are going to discuss about ipv6 network addresses. ipv6 network addresses are like IP version 4 addresses in the sense of being logical. They can be configured and assigned on our devices according to our requirement. Okay, but it should be done correctly. Though we are currently using IP version 4, why do we need IP version 6? According to these 5 entities, which are called regional internet registries, IP version 4 public IP address spaces is going to get exhausted. So how can we connect to the internet without public IP addresses, isn't it? So for that reason we need IP version 6. Actually, the public IP addresses is divided into 5 subspaces and controlled by these 5 entities all over the world within their region. Okay, according to Erin, it is going to get exhausted in July 2015, and according to LACNIC, it is going to get exhausted in 2014 in South America. According to APNIC, it is going to exhausted in April 2011 in Asia, and so on. So to solve this problem, we need IPv6 address. Okay, the address space provided by IP version 4 is 2 to the power 32, which is 4.3 billion. Though it is large very before. Okay, today, due to current usage of internet, which is increasing very rapidly in exponential way, we need large IP address spaces. Okay, the current 4.3 billion address space that is provided by IP version 4 is not sufficient. Okay, due to development of the devices, smart devices, and the technologies like Internet of Things, okay, uses of IP version 4 addresses are increased exponentially. In Internet of Things technologies, one machine try to communicate another machine without human intervention using specific IP addresses on them. So to solve this problem, we need IP version 6 addresses. Okay, and IP version 6 address provide 2 to the power 128-bit address space, which is 340 endecillion addresses, which is very large in comparison to IP version 4 address spaces. Okay, now there are some issues within NAT in IP version 4, which is also solved by IP version 6, and that issues is when source tries to communicate with destination, that packet get translated, that packet source addresses get translated to the public IP address. Yeah, we are already familiar with that. The source private IP address get translated to the source public IP address, which generally translate the real IP of the source. So this problem gets solved by IP version 6. And how? Because in IP version 6 there is no technologies like NATing, because it's already have in IP version 6 already have large IP address spaces, so we don't need NATing like technology there. Okay, now let's move forward. These are the 3 techniques that we can use to migrate IP version 4 to IP version 6. The first one is dual stack. In this dual stack technology, we can assign both IP version 4 and IP version 6 addresses to the networking devices and in user devices. But one thing that should be kept in mind is that these devices must support both IP addresses, that is version 4 and IP version 6. In tunneling technique, when we use tunneling technique, when do we need this? In this technique, actually, when the source is in IPv6 only network and destination is also in IPv6 only network, and the network in between them is in IP version 4, we can use tunneling. Actually, what happened here is the IPv6 packet is encapsulated inside IP version 4 packet. When this packet moves from this source to this tunnel, it is encapsulated within IPv4 packet, and finally it will reach to this router, which is running dual stack, and this router decapsulate that packet and forward the pure IPv6 packet to this destination. In translation technique, what happened actually is we can use NAT64 router which translate IPv6 packet to IP version 4 packet and vice versa. This is like NATing in IP version 4. Now let's move forward. This is basic representation of IPv6 address in 128-bit lane. As we know that IP version 4 use decimal address, okay, decimal digits. In IP version 6 we use hexadecimal digits that can run from 0 to F. Okay, and this 128-bit lane IP version 6 address is divided into 8 different groups using this column. Okay, and each group is called hex text. Okay, and each hex text contains 16 bits, and its range can move from 000 to FFFF. Yeah, okay, let's move forward now. Okay, this is basic representation of IP version 6 address. You can see it is very lengthy. Okay, can we hold this original value and squeezes? Yeah, definitely, but for that we have to follow some rules. Okay, these are the rules. This is the pure IPv6 address, and here we can see we are following this rule 1 and omitting leading 0. As you can see, this 0 deviate can be written as deviate, and this leading 0 can be omitted, and similarly 0 to 0 can be written as 200. Okay, but we can't use write 2001 as 21 because it will lose its original value. Okay, and we can see here this 4 consecutive hex digits of this hex text can be written as 0. Okay, in this way we can squeeze IPv6 address. Okay, so here we have also squeezed 4 hex digits which are in 0 format in this hex text into single 0. This is rule number 1. Okay, now let's move to rule number 2. What we can do is we can omit all 0 segments. Like here, if we have consecutive hex text which are in 0 format, we can represent it as double colon. Okay, similarly this consecutive zeros in hex text can be represented by double colon. But one thing that should be keep in mind is we can't use these double columns in more than one places in single IPv6 address. That is, we can't use double colon here. Okay, in place of this double 0, and we can't use this double colon in place of double 0 at the same time. Okay, here we can see that we have reduced this number of zeros of these consecutive zeros of this hex text by double colon here. This is also rule number 2. Now let's see different type of IPv6 addresses. IPv6 has these 3 different types: unicast, multicast, and broadcast. Unicast is like one-to-one communication. For that we use unicast IPv6 address. Multicasting is used when single IPv6 packet is need to be transferred to multiple destination. We use multicasting there. Okay, and anycasting. Why do we need anycasting? Let's take one example. Generally in anycasting, the server content is replicated into multiple servers and they are kept in far distance apart. Okay, and same anycast address is assigned to them. So when requester is try to send request to the server content, it will first try to send that request to the server that is closest to one, and if it is unavailable, then that request is transferred to the next server that is closest to that server. Okay, in this way it will help to reduce the downtime and protect from attack like DDoS attack. Okay, now let's see. This is the IPv6 prefix length example. In this example we can see 128-bit IPv6 address is divided into 2 parts. First one is prefix and second one is interface ID. Okay, and interface ID is used to represent the host within that subnetworks uniquely. Okay, let's move forward. Okay, these are different types of unicast addresses, IPv6 unicast addresses. As you can see in this diagram, the first one is global unicast. It is like public IP address spaces which is unique in the internet, and next one is link local, which is used to communicate with other device in the same local link. It means that it cannot, the packet which is using link local address can't cross the same local link. Okay, it can't cross the network. Okay, it can't reach from one network to another network. Okay, from one router's one interface to another interface. And unique local address is like private IP address spaces in IPv4. So this IP addresses can move packet from private IP to the public network, that is in internet. And you can see the loopback address here is shown in IPv6 format. It is :1/128. Okay, this is loopback IP address format in IPv6. Let's test it. 127.0.0.1. This is loopback IP address in IPv4 and is providing me reply also. So see, I am requesting I am sending echo request to 127.0.0.1 and it is sending me echo reply. Similarly, I can ping here also ::c 1. Okay, it is also providing me, it is also sending me echo reply. How it is possible? Because this request reach up to the NIC card. It can't cross the NIC card. Okay, it can't cross the NIC card and reach to the cable. My NIC card is self reply. Okay, without sending that packet to outside of the NIC card, my NIC card itself provides me echo reply. So this helps to check whether my NIC card is working properly or not. Okay, and unique local address is like a private IP address space, and its range is from FC00::7 to FTFF::7. Okay, there are different types of ipv6 linked local unicast address example. See, in this example we can see that this device is trying to communicate with this device, okay, using linked local address, but that request can't cross the router's this interface and can't reach to another interface of this same router. Okay, so its scope is within this link only, within that network only. Okay, and its range is FE80::10. Okay, any address that start from FE80::10, okay, it is called linked local address. Now move to next slide. This is the basic structure of the ipv6 global unicast address. As you can see in this diagram, it should start always from 001. First 3 bits of global unicast IP should be 001, and it should be fixed for global unicast address, and it is represented by 200::3. Okay, when we keep first 3 bit fixed by 001, it will provide us 2000::3 prefix, and this whole global routing global unicast address can be divided into 3 parts: global routing prefix, subnet ID, and interface ID. And global routing prefix is of 48-bit length and is provided by the ISP to the organization. Okay, a subnet ID is used by the organization to subnetwork it's with the internal network. A subnet ID is of 16-bit length. Okay, so it can provide 2 to the power 16 subnetworks. Interface ID is used to uniquely identify the end-user devices, network devices, or host devices within that subnetwork. Okay, let's try to configure one lab. Okay, let's see here in this lab. I'm going to configure these 2 routers. Okay, I'm going to configure 3 different addresses within same interface of each routers. Okay, okay. See, let's see. Let's say router 1. I'm going to gigabit interface, ipv6 interface, ipv6 address 2000::1:1/64. See, this is global routing prefix, and this is subnetting part, and this is interface ID. Okay, I am assigning global unicast address here, FC00::1/64. Now I am assigning unique local address to the same interface. So multiple ipv6 addresses can be assigned to the same interface simultaneously. Okay, in ipv6. Now I am assigning linked local address on this router interface. Now check it. So ipv6 interface is okay. Using this command, I can check whether that interface has been assigned with the series IPs or not. Yeah, it has been assigned correctly. Now let's assign ipv6 addresses in second router interface gig 00 ipv6 address 200::1:2/64 ipv6 address FC00::2/64 ipv6 address FE0::2/64. No, okay, it's linked local. Okay, in this way I have configured global unicast address, unique local address, and linked local address in the same interface of the router 2 also. Now let's try to ping to the next device 200::1:1. Let's see. Yeah, I can ping now. I can ping to global unicast address of another router R1. Now ping to, let's ping to unique local address. See, I can also ping to the linked local address of router 1 from router 2. Now let's ping to FE80::1. See, it's asking for output interface because different linked local address can be specified to different interfaces of the same router. Now let's specify the interface. Now see, I can ping from this interface to R1's linked local address. In this way, I can configure and verify the assignment of the ipv6 address on the networking devices, Cisco networking devices. Okay, thanks for watching this video.